Hey everyone, welcome back to the Physics Unit 1 motion videos. Here we're going to be looking at something called the vector component method, which we can use to solve any type of vector-related problem when we're working with problems that have, are situational problems where we have more than just two-dimensional movement. Say just moving frontwards or forwards and backwards, left and right. So here we're going to be looking at examples where we're moving at different types of angles that are not just simple ones like up and down, left or right. Here we're going to be looking at an example from your notes, which is our first vector component method example. So a football player is hoping to score a touchdown by running a complicated play. He runs 5.0 meters north 36 degrees east, then changes his path to run 12 meters north 51 degrees west, where he meets a block and is forced to run 15 meters south 73 degrees east before he is tackled. So here we're going to determine the resultant vector. And so we want to know, did this player have a successful play? So did he move forward overall, or did he lose, lose some distance? And so essentially with our vector component method, there's 5 steps that we can follow. And with these 5 steps, what we're trying to do is we're going to take all of these crazy angled values and we're going to create a right triangle by finding their x and y components. So our first step into completing our vector component method is we're going to write down our information, and then we're going to be determining the principal angle for each of those vectors. And then we will be using those principal angles shortly to help us find our x and y components, which is step number 2. So the first bit of information here is we were told that the player runs 5.0 meters and it's north 36 degrees east. So here we'll be finding the principal angle, and our principal angle is essentially our angle from the x-axis. So just to do a quick rough sketch of what this north 36 degrees east looks like. So here we're starting with our north direction, and we're going 36 degrees east. So this right here is 36 degrees east. But what we want is, we want this angle right in here, because that is our principal angle. It measures from our positive x-axis and goes counterclockwise. So to find that principal angle, all that we're going to do is we're just going to take 90 degrees and subtract that angle, which is 36 degrees, which will give us a total angle of 54 degrees. Then we're going to do the exact same for the other 2 pieces of information that we have. So our next bit that we were given, we have 12 meters, and that one there was north 51 degrees west. So looking at a rough sketch of what this might look like, here we're working with north and we're going 51 degrees in the west direction. So that's going to be over here in quadrant 2. So to find your principal angle, which goes from your positive x-axis all the way over to this terminal arm, we're going to take 90 degrees and add this little angle right here, which was 51. So we have 90 degrees plus 51 degrees, which will give us a principal angle of 141 degrees. Then with our third bit of information there we had 15 meters, and it was south 73 degrees east. So doing a rough sketch here, we have south and we're going towards the east direction, which puts us down into quadrant 4 here. So to find that principal angle, we'll take 3 quadrants worth of angles, that's 270 degrees, and add it with the 73 degrees here. And that gives us a total of 343 degrees for our principal angle. So that bit of information was really important there, because now what we're going to do is we're going to break each of these little segments up into their x and y values. So we're going to find the vertical and horizontal components that will help us create a right triangle. So we're going to start by looking at our x values first. And so to find your x values, we're going to take a variation of the cosine ratio, where we have our, say, f of x value is equal to the vectors. So say, for example, our first one was 5. So 5 times the cosine of that principal angle. So in our first example here, we had 5 meters as our total vector there, so 5.0, times the cosine of that principal angle, which we calculated was 54 degrees. And if you guys put that into your calculators, you should get a rounded value of about 2.9. And this one here is in meters if you're trying to keep track of your units. And we've also got correct sig figs here, so we're good to go. Then we can do the x component of our second part. So f of x here is equal to, so our force in that one, or that vector, sorry, was 12 meters. And the principal angle was 141. And that we should get a negative 9.3 meters in our calculator. And we get the negative because it indicates it's going the opposite direction. So for a positive 2.9 here, it's indicating that's probably going to the right there. So with negative, it's going the opposite direction. So this one here will be going to the left, or I guess in our case when we're using our compass directions, this one here tells us that we're actually traveling west. The directions itself are not as important as making sure we have the positive and negative symbols in there correctly. And then just to we'll squish in our third step, or I guess our third vector here. And that one there was 15 meters. And that principal angle was cosine of 343 degrees. So plugging that into our calculators, we get that that distance there, that x component, so your horizontal, is a total of 14 meters, and it's positive, which tells us that we're going east. Now we're going to copy, paste, repeat this exact same process for our y component, except this time here we're going to be using the sine ratio. So here's our y values. And so your work will look almost identical to what we saw in our x component, but the only difference here is that we're going to switch cosine with sine. So we'll call this f at y instead. So there we have the 5.0 times the sine of 54 degrees. Plugging that into our calculator, we should get a rounded value of 4.0 meters. For our second vector, we had 12 times the sine of 141 degrees. Put that into our calculator, we should get 7.6 meters. For our third component, just going to scroll down here a little bit. So here are the magnitude. We traveled the distance of 15 meters. We're going to times it by the sine of our principal angle, which was 343 degrees. Plugging that into our calculator, we should get negative 4.4 meters as our total vertical change. So once again, just remember that our positive indicates that we're traveling up or forward or north, and so negative would indicate that we're traveling down, or which would be our south direction. So now that we've broken everything into their x and y components, now what we're going to do is we're going to find the total sum of each of our x components and then the sum of our y components. So we're trying to make this into one nice triangle or right triangle. And so here would be our horizontal. So that total change would be our horizontal, horizontal aspect of our right triangle. This one here is going to be our vertical. And then what's going to happen is that overall the total change is this hypotenuse here. So we're going to have our x components, our y components. Then if you guys can see where we're going from here is that we are going to use our Pythagorean theorem to solve for our magnitude. And then we can use the trigonometric ratios to help us find the angle at which you've changed. So what we're going to do is we're going to add up our x components first. So this will be the total x change from where you originally started. So you're going to take your first component, which is 2.9, add it with that negative 9.3, and then add it with that 14. So 2.9 plus negative 9.3 plus 14 is 7.6. And I am going to keep track of my sig figs here. Remember, with your adding subtracting rules, you want to go to your least precise digit which in this case here is actually to the nearest whole number, because 14 is 1 digit to the left, while the other two are 1 digit to the right. So I'm just going to keep track of my sig figs here by underlining that 7. So for finding that sum of your y values, you're going to do the exact same process. So you're going to take that 4.0, add it with the 7.6, and add it with that negative 4.4. So adding up all those numbers there, we should get a total vertical distance of 7.2 meters. All right, and then just to talk about that positive negative aspect again. So just remember that when we have a positive, that's indicating we're going on a positive x-axis direction, which means that we're heading east there. And then for that y component here, we're moving up, which is our north direction. So then what we can do from here is that now that we have our total x component, we have our total y component, now we go ahead and use that, our Pythagorean theorem, to solve for a magnitude of the resultant vector. So I'm just going to draw out our right triangle here. This is also going to help us out for our next question here. And I typically like to draw my vertical components first, so that way I can have my compass direction being in terms of a north and south direction. So I'm going to draw this north one first, which was a total of 7.2 meters. And then we were traveling east 7.6 meters. So our resultant vector starts from the bottom of the original and then goes up to the tip or the head tail of our second vector. So here, when we're solving using the Pythagorean theorem, we'll be solving for this magnitude here, which is your hypotenuse. And then in step 7, we'll be finding that angle, which will be from that beginning position to your end. So using our vector component method, we're going to take the square root of your x value squared. So our x value here was 7.6 squared. Then we'll take our y component squared, which is 7.2. And then we can simplify each of those before actually putting anything, or I guess square rooting and taking the sum of any of those numbers. So squaring each of these numbers, 7.6 squared should give us 57.76 plus our 7.2 squared, which should give us 51.84. And I'm just going to keep track of sig figs here very quickly, just because it'll be important for when we're doing our significant digits. So our 7.6 here had one significant digit, and our y component had two significant digits. So here when we do our square, we need to stick with that one significant digit for our x component, and then 2 for our second. So then when we add them together, so when we add them together, we should get a value of 109.6. And then using those adding and subtracting rules for significant digits, this is 1 digit to the left, this is 2 digits to the left, so we need to go to a total of 2 digits to the left there as well, which means that we actually now have 2 significant digits for our answer. So we can go ahead and square root that, and with our rounded values, we should get about 10 meters as our answer. And we want to make sure that we have 2 sig figs, so I'm going to indicate that with a bar over top of it. So now what we're going to do is, now we have that magnitude, now we need to find a direction. And so with this one here, we're going to use our tan ratio to solve this. And so with this one here, we're going to take our opposite side and then divide it by our adjacent. So if we're looking at this one here, it is our opposite to the angle is our x component divided by that y component. And we use, typically for our principal angle, we use this Greek letter sigma with an r to indicate the reference angle. So it'll be equal to the tan inverse of our x component, so 7.6, divided by that y component, which is 7.2. And our calculator will give us 47 degrees as an answer. So from this, we can say that the player advanced 10 meters, and our direction here is we're going up and to the right, which means we're going north 47 degrees east. So did the player advance? Well, yes, they did. They advanced 10 meters northeast.